So what is ADCP? So ADCP is a thin layer that sits in between the TCP layer or the transport layer and the IP layer. Okay. Yeah. So ADCP sits here. Okay. And then this ADCP layer would have 4 states: normal, disconnected, congested, and lost. Okay. So we'll consider each of these in sequence. All right, so now just go back to these. So basically in these problems, TCP will have packet losses or will time out or receive duplicate acknowledgement. That means it indicates packet losses as well. But these are not caused by congestion, right? So how does the TCP sender knows that, or ADCP knows that a packet is lost because of congestion or because of any of these issues? All right, so we'll see this later. For congestion, at the network layer, IP layer, there's something called ECN, explicit congestion notification. And when this flag is set in the IP packet, all right, so that indicates congestion. So when a router experiences congestion at the router, it will set this flag in the IP packet. All right, it will set this flag in the IP packet. And this flag indicates that the current router is experiencing congestion. And that's how TCP and ADCP knows about congestion in the network. Okay, so that's for this case. And for this case, right? And for this case as well. So if a packet's lost, but the flag is false, it doesn't set, it's 0, right? False is 0. That means the packet is lost because of this, or maybe because of the route changes, for example, or maybe because of packet arriving out of order, right? So when TCP receives duplicate acknowledgement, and this flag is 0, so that means it's not because of congestion, okay? But when a packet is lost and this flag is 1, so that means the loss is caused by congestion, okay? So that's how TCP and ADCP knows whether there's congestion in the network or not, okay? All right, so let's go into each of these states. All right, so now what we're doing is we see how from the normal states we go to disconnect, or from normal to congested and to loss, and then how to go back to normal. Okay. All right, so first in the normal states, okay, if there are packet losses, right, so that means TCP and ADCP will time out. Okay. So if it's time out, then ADCP will put TCP in persist mode. All right. Now at this point, it had to check the ECN flag first. Okay. And in this case, the ECN flag is 0. That means there's no sign of congestion. So the assumption is the packet is lost because of error rate, high bit error rate. Okay. All right. So in this case, ADCP will put TCP in persist mode. That means TCP doesn't do anything. ADCP, okay, let me see why I can, all right, yeah. So in this case, how does ADCP and TCP know whether a packet is lost or not? So basically the retransmission timeout is about to expire, right? So if it's a packet is not acknowledged, the retransmission timer will expire, or TCP receive 3 duplicate acknowledgement, right? So this is equivalent to a negative acknowledgement. Sorry, 1 second, please. So in that case, ADCP will put TCP into persist mode. Okay. Okay, so, sorry, please excuse me for 1 minute. I'll just get some hot water first. I have a sore throat. Yes, 1 second, please. All right, I'm sorry. So we're back. All right, so so in that case, in this case, the retransmission timer is about to expire, or the sender received 3 duplicate acknowledgements for a data packet. So it can assume that this packet is lost, right? Or the packet that is timeout will be lost soon. Okay. So in that case, ADCP will put TCP in persist mode. That means TCP doesn't have to do anything. ADCP will transmit the unacknowledged segments from the TCP buffer. Okay, so that means the ADCP will retransmit the packets that has been timed out, or this packet here. All right, and then ADCP maintains its own timer for the segments, for this segment and this or this segment. Okay, because if it expires again, then ADCP will do the same thing, retransmit, right, and maintain the timer, and then retransmit again. Okay, so this may be caused by, if this happens again, so this may be caused by a route that is broken, node mobility, and then it takes time to rebuild the route, the new route, right? So it keeps times out. So in this case, TCP will take care of this. It does not reduce the window size, just retransmit the lost segments. Okay. And then when a new acknowledgement arrives, so that means the receiver received the retransmitted packet, and it sent a new acknowledgement. So in this case, we can assume that either the route has been established, or the receiver have received this successfully. So in this case, ADCP will forward the acknowledgement to TCP, and both of them return to the normal state. Okay, right. So ADCP retransmit segment in the buffer, and then new acknowledgement comes, and ADCP go back to the normal state, and TCP will go back to the normal state as well. Right. All right. So this can solve the problem of packet losses caused by high error rate, by route changes, route recomputation, okay, or by packets arriving out of order because of multi-path routing. Okay, so now we'll talk about how we solve the problem with the congested state. All right. So as I said before, congestion is detected by ECN flag in acknowledgement and by data packets. Okay, so every router would examine the IP packets, and if the router is experiencing congestion, it will set this flag to 1 in that IP packet, and then ADCP will examine this flag and determine whether there's a congestion in the network or not. Okay, so that's the job of ADCP. Now, one thing we have to be cautious here. The use of ECN flag is not universal in the sense that some routers may or may not implement this ECN flag. Okay, that means it would experience congestion, but it does not set the flag. But it is not a universal implementation. Okay, and in the paper they address this problem in detail. We're not going to detail here, but just as a caution that not every router would implement this. Okay. All right. So if this happens, then it happened, then ATCP knows that there's real congestion in the network. So in that case, it just stay quiet. It does not interfere with TCP's congestion control. So TCP will invoke congestion control as before, reduce the window size, right? And then transmit using either the original scheme or to using fast retransmit, either one. And in that sense, now TCP is in control. ATCP just stay quiet because there's real congestion in the network. Okay, and after TCP retransmit the lost packets, reduce the window size to reduce congestion, and TCP transmit a new segment, then both of them, ATCP and TCP, will return to the normal state, right? So this ATCP return to the normal state. Okay, so you can see in this diagram here, when in the normal state, if ATCP receive the ECN flag, it will go to congested state, right? And here, TCP will take control over to reduce congestion. And after TCP transmit a new packet, after TCP reduces congestion, transmit a new packet, ATCP return to the normal state. All right. Now, when ATCP is in the lost state, if it receives an ECN flag, I mean, it receives acknowledgement or data packet with an ECN flag set to 1, then yes, it goes to congested state as well. All right. So that means now it had to stay quiet and let TCP handle congestion. Okay, the same thing here for both of these. All right. All right. So now disconnected network. How does ATCP knows whether the network is disconnected or partitioned? Again, this is done using a network layer feedback. So when the network is disconnected or partitioned, there is an ICMP message, destination unreachable, generated at the IP layer. Okay, this is done by the IP routing at the IP layer. So that stands for Internet Control Message Protocol. Okay, so when destination cannot be reached, the IP packet, the router that cannot send forward the packet anymore will generate an ICMP message and send back to the source. Okay, so in that sense, this kind of message can reach every node from the path from that router up to the source. And if so, in this case, when a node that cannot forward a packet because it cannot reach the destination, it will generate an ICMP message. When ATCP receives this ICMP message, it will enter the disconnected mode. All right. So that means it doesn't do anything. TCP is put into the persist mode. That means TCP doesn't do anything either. So basically, both of them have to sit there and wait until the network is reconnected. They stop transmitting. They couldn't do anything until the network is reconnected again. All right. So at the same time, ATCP will tell TCP to set the window size to 1. All right. Why have to set to 1? Because after the network is reconnected again, all right, after the network is reconnected, the source has to build or to compute a new route from the source to destination. And now we have a new path, right, from a source to destination. Basically, this is a new connection. You can consider this as a new connection, completely new connection. So we have to start TCP from the beginning. That means the window size have to start from 1, increase to 2, and then 4, and then 8, right? That's why the window size now have to be reset to 1 because of that issue. After the network is reconnected, a new route has to be built. Basically, we establish a new connection. So the window size must start from 1. Okay. And while they are sitting waiting, TCP periodically generate probe packets to reconnect with the receiver. Okay, so that means the sender will keep sending probe packets periodically saying, are you there? Are you there? Are you there? Right? After a while, maybe the network is reconnected. So in that case, the receiver will receive this probe packet and it will respond with a duplicate acknowledgement or data packet, right? Will respond and then a new route would be recomputed. And in that sense, it will respond with a duplicate acknowledgement or data packet using the path. And now ATCP and TCP will return to normal state. So basically now what it means is the network is reconnected, a new route is computed, and now they can start transmitting again. Okay? And of course, now TCP will set the correct value for the congestion window for the new route, right? Because basically we just established a new connection, a new TCP connection. Okay, right. And that is how we use a diagram before. So let me see here. Okay, so it's received destination unreachable. Okay, from the normal state. And it go to disconnect and set window size to 1. Okay, and when it receive a duplicate acknowledgement or packet from the receiver, that means the route has been reestablished. So now we go back to the normal state, right? And the same thing as before, when ATCP is in either congested or lost state, if it receives a destination unreachable ICMP message, that means the network is disconnected. Now it have to go to the disconnected state, right? Okay, and this is the same diagram as this one here, but it doesn't have any color, and that's, yeah. So you can see that if we take a look at this diagram, right, it seems very complicated. It's not easy to remember. But if we break it down to previous diagram, right, you can see it's easier to remember this way, right? You can draw the diagram easier this way, right? Yeah. Okay, so is ATCP successful or not? Obviously, it's successful in the sense that it maintain end-to-end TCP semantics. It doesn't change any TCP semantics. It's compatible with traditional TCP and it's invisible to TCP. Okay. Of course, the disadvantages are the dependency on the network layer protocol. So we said it rely on the ECN flag, right? And it rely on the ICMP message, destination unreachable. And some routers may not even implement the ECN flag either. But it depends on the network layer protocol to detect route changes and partition and congestion. And of course, it has another overhead of the ATCP layer, right? So now we have basically one more layer added to the TCP IP protocol stack. So some more overhead there, right? Okay, so now we just go briefly over some example experiments to show how ATCP performs compared with original TCP. Okay, so these are in the paper, and I will post the paper. Yeah, I'm not sure if I post the paper, but if I forget, I will post the paper. the paper from which the experiments in which the experiment were described. So in this experiment, they simulated a 4-hop network, right? So that means 1, 2, 3, 4. So that means they use 5 computers and they use 5 Pentium PCs. So it's been a very long time ago. They use 5 PCs to simulate a 4-hop networks. And the channel capacity is 32 kilobits per second, which is a low bit rate as well. And they simulated hop by hop delay. So that means the delay from here to here will be increased from 10 millisecond to 20 millisecond, 30 millisecond, 40 millisecond, 50 milliseconds, right? So this hop delay will impact the round trip time, right? And the round trip time will affect the retransmission timeout, okay? And they assume a bit error rate of 10 to the power minus 5. Okay, so this is a good number for, basically the best number for a wireless environment. They assume a file transfer of 1 megabytes. And for each data point like this, they will run 20 experiments, and then they take the average, right? And the confidence interval is 90%, okay? All right, so, and this is the line for ADCP. So this line is for ADCP. And this line is for TCP, all right? So the first observation is that, and this, the x-axis indicates the hop to hop delay, the average hop to hop delay in millisecond, okay? And the y-axis represent the transfer time, okay? The transfer time of this file, okay? How long it takes to transfer the file. And you can see that the first observation is it takes TCP much longer time to transfer the file. For ADCP, it's around a bit over 400 seconds to transfer this file, over 400 seconds. And for ADCP, it's around 900 here. If we have a low delay, to around 1900 here, right? Around 1900, yeah. So you see it takes longer for TCP to transmit the file. So that's one observation. The second observation is that ADCP basically has a unchanged transfer time, right? So it's basically constant. But for TCP, as the hop delay increases, the transfer time increases as well, okay? So that means for ADCP, it's scalable. Scalable in the sense that you increase the hop delay, but the performance doesn't change. TCP is not scalable in the sense that as you increases the hop delay, the transfer time also increases, okay? And the reason for TCP to perform much worse than ADCP is because we can see here from this graph, the congestion window size, okay? So this is the time, right? So as we run the experiment, this is time 0 up to time 200 seconds, for example. And this is the congestion window size, right? So you can see that with TCP original, without any improvement from ADCP, the window size, you can see at the beginning, it go up, right? And then there's a packet loss here for any reason. It go down to 1, and then it goes up. And then again, for any packet loss, it go down again here, and then go up. Packet loss happen, goes down. So you can see it oscillates a lot, right? And many times it had to go down to a very low value here, okay? And that's why it cannot transmit as fast, because the window size will limit the number of packets that TCP can send without acknowledgement, right? On the other hand, the window size for ATCP almost remain constant, right? You can see here, it almost remains constant here. All right. And that's why it can send a lot, because the window size is not reduced by packet loss rate. Okay, and that's why ATCP can perform much better. It requires much less time to transfer the whole file. Okay, so in this case, we assume that the packet losses are caused by high bits error rate, right? So in the next experiments, now they introduce congestion. Okay, so not only bit error rate, but also congestion, both of them happen at the same time. So as before, the bit error rate would be the same here. So basically almost everything is the same. The only thing now is they add congestion, and congestion is every 200 milliseconds, right? So they would have some node in, injected packets into the network. And it happened every 200 milliseconds for every 5 seconds. Sorry, 200 milliseconds of congestion for every 5 seconds. That means during the experiment, they could have about 80 congestion events, right? And again, you can see that as we increase hop-to-hop delay, so this is a hop-to-hop delay, the x-axis, and this is again the transfer time for the file. ATCP has a much lower transfer time compared with TCP, right? So ATCP is here, and so the TCP is here, right? Much lower transfer time, and basically almost constant. It increased only a bit here. With TCP, as the hop delay increases, the transfer time also increases significantly. All right, and again, that goes back to this problem here. Okay, let's go back to this problem, because every time there's a packet loss, TCP could reduce the window size to 1. That's a problem with TCP. Okay, and in this case, another experiment in which we have bit error rate, high bit error rates, and partition. And the network is partitioned for every for 1 minute for every 5 minutes. Okay, again, ATCP here has lower transmission time, and TCP higher transfer time for the whole file, right? This is almost constant. This is increases significantly as the hop delay increases, or the round trip time increases. Okay, and then in this example, they combine all 3 factors: high bit error rate, congestion, and the network partition. Okay, and the file is also 1 megabyte per second, 1 megabytes in size. They ran 2 experiments. On the left here, they would have interfering traffic of 8 packets per second. That means the intermediate nodes, right? So we have the intermediate nodes here. So in addition to this connection, the intermediate nodes here would inject 8 packets per second. And on this side, they would inject 16 packets per second, right? To simulate, let's say, congestion, to simulate, let's say, collision or any other impact on the file transmission, the file transfer. Okay, so you can see that, and this is the time to transfer this file. In the first experiment, obviously, this ATCP takes much less time to transfer the file than TCP, right? We've seen this before. In the second experiment, again, ATCP takes much less time than TCP to transfer the whole file. Obviously, when we have more interfering traffic, then we would take more time, right? So that's why TCP here is a bit higher than this. TCP is higher than this, all right? So it makes sense. All right, so in this example, we combine all 3 components: high bit error rate, network partition, and congestion. Okay, All right, so next, so this is a summary of ADCP. So ADCP is a thin layer between IP and TCP, and it maintains end-to-end semantics. It does not interfere with TCP congestion control behavior when there's network congestion. The disadvantage is it depends on the network layer to detect route changes and partitions. Okay, so that's the disadvantage of ADCP. Okay, and these are the papers. So I'm not sure if I posted this paper or not, but I will post this paper if I haven't posted. And in here, you would have more details about the lecture we just discussed here. Okay, all right. So that's the end of the ADCP. Okay, so this is the end of ADCP. So let's take a break for about 5 minutes, and then when we come back, yeah, I will answer your question about the midterm test. All right, but before we leave, I just say very quickly. 1 second. Sorry. Let me show the slides again. This slide. Where is it? Okay, so for the test tomorrow, so please arrive a bit early, let's say 11:25, right? 11, yeah. But whenever you arrive, please wait outside the labs, right? And then the TA will show you to your seats because the lab is small, and we have to rearrange the seats. So the TA will show you the seats. So don't come in the lab. Just please wait outside. Okay. So that's one thing. The second thing is there should be no question during the test, right? Unless you find an error in the handout. And for obvious reason, we have to whisper because we don't want to talk too loud because we don't want to disturb other people. But if we whisper, we have to be very close, and it's not very good during this pandemic, right? So we should not be talking too close to each other. That's why no question during the test, unless you find an error in the handout. Okay, so that may happen. That happened in the past during the printing process. Let's say one character or one letter or one digit was removed or was messed up in the handout during the printing process. So in that case, you can report it, and we will correct that for the whole class. But otherwise, please do not ask questions during the test, again, for health and safety reason. Okay. All right. So yeah. So we'll take a 5-minute break, and I'll be back if you have any question. Yeah, there's no quiz today. All right. There's no quiz today. So when we are back. Feel free to ask questions about the midterm test. All right. So we'll be back around 3:40. Okay, we'll be back around 3:40 to talk about the midterm test if you have questions. All right. Now, if you decide to leave after this, then I'll see you tomorrow. Please print a photo ID, pens and pencil, and a mask. Don't forget a mask. And please arrive early if you can. Okay. And please wait outside the lab. And then the TA will show you to your seat. All right. Yes, you can print a calculator, but it has to be a non-programmable calculator, like a simple one, a simple calculator, not a fancy one. Yes, you can print a calculator. That's fine. All right. So so if you're leaving now, then I'll see you tomorrow. And have a nice afternoon, and good luck with your study for tomorrow. Okay. All right. So we'll be back at 3:40 if you need to ask questions about the midterm test. Okay. Okay, so okay, so I'm back. Right, so for the midterm test tomorrow, of course you already know what you have to study, right? The lecture notes, everything from the beginning up to and in sorry, not today, sorry, last week, because that was from last week lecture, but not today's lecture. Okay, so this slide was from last week. Okay, and then if there are sections in the books or papers, you should read them as well. Labs 1 and 2 and the practice questions. Okay, so any question you want to ask about the midterm test? What is the format of the question on the midterm? It's very similar to the practice question I posted earlier. There's a set of questions I posted earlier. So what kind of question will be like multiple choice? There will be no multiple choice question this time. Okay, no multiple choice question this time because we don't have a computer. We don't have a computer to do it on eClass. So the question would be the format is similar to those in the practice questions. Okay, all right. How many questions will there be? So basically, this is one of the questions that I don't like because I can give you only 2 questions, but it may have several smaller questions. Or I could give a bunch of smaller questions. So the number doesn't make any sense in this case. I'm not going to say how many questions, okay, because it doesn't have any context. All right. Did you post question DSR and ODP in practice question? Yeah, sorry, I haven't been able to find any question for the SR and AODV, but they could be, the format could be similar to those posted, right? So instead of, you can ask the same question, but applied it to DSR or AODV, okay? Right, so all the questions will be with short and long answer handwritten, exactly. Is there any question about abbreviation? Of course, we may use abbreviation in the question. So you must know what it means, right? So if you can see, we could write, let's say, BSS. BSS means basic services, for example, WPA, WAP, right? WEP, for example, TCP, RTT. What is RTT? Round trip time. So you have to know these abbreviations. Okay. Okay. Will formula be provided in? No, we will not provide any formula. So you have to memorize the formulas. There are not many. I think only 3 or 4 in signal propagations. Okay. No, that we will not provide the formula. You have to study the formulas. Okay. Right. Okay, any other question? Yeah, so can I ask a question not regarding the exam? Yes, Joshua, yes, you can ask, and after that will be Ahmed. Yeah, you can speak, Joshua, if you want to ask a question is about the exam. Yes, not regarding the exam. Okay. It's good regarding the lossy channel and congested. Okay, so the ATCP. Okay, so that yeah, I can answer that question. All right. So you want to go over the ATCP again? Okay. All right. So I will answer that. All right. Yeah. So let's answer the midterm question first, right? So people can leave and then we'll continue with the, yeah, I agree. Okay, so let's see, the next person who want to ask about the material is Ahmed. Ahmed, you have a question? So if a medium is busy and the channel was in back of counter, right? Will the counter reset or simply pause and resume? And we're talking about AO 2.11 medium access control. Are we talking about AO 2.11 access control, Ahmed? Yes, okay. Yes, the counter will pause and then resume. It does not reset, okay? And we talked about this before. If the counter will reset every time it had to wait, then it may never be able to use the medium. Right? If it had to reset every time, that it may never be able to use the medium. Okay, in the worst case. All right. Okay. Yeah, you're welcome. Next, Ruchi have a question. Will the difficulty be similar to the quiz and homework question or harder? Yeah, it will be similar to the quiz and the practice question. Yes, will be maybe 1 or 2 questions would be harder, but the majority would be similar to the quiz and the practice question. Okay. All right. Shabash, can I ask a question about the lectures? Okay, yes, you can. Yeah, Shabash, you are next.
Hello, Professor. Can I speak up?
Yeah, sure.
Okay.
Yeah, it's even better. Yes.
Okay, cool. My question was about the security slides, actually. So there are like slide 39 to 42. There are some graphs and pictures, but I cannot understand them. Is it going to be possible to quickly tell me what are these figures about and how is the process being done in these pictures?
Okay. Sorry, just 1 second.
I can share my screen with you if you.
So I have the screen. I have the screen. Okay.
Okay.
All right. I have the screen. Okay. Right. So yeah, so let me see if there's any shorter question and then we go there because that may take a bit longer.
Okay. Right? Yeah, definitely.
Yeah, sure. So I think after this would be Joshua and then Ahmed already. Ismail. Will the midterm question be similar to the practice question or the format? The format is similar. The format is similar, not the question. Okay. It's the format, not the question themselves. Okay. But if you study those questions, so that would help you understand the material better, right? So the format will be similar, not the question. Okay. Right. Okay. So no more question, right? Yeah. So I will go through the slide 39 in security. Okay. 39 to which slide?
To 42.
42. Okay. All right. Okay. So let me share the screen. Okay. Yes. All right. Can you see the screen?
Yeah, I can see.
All right. So this slide indicates the basically it's a summary of the authentication process. Oops, sorry. In WPA, right? The authentication and the key generation process. All right. So let me make it bigger. Okay. So basically, the first part here is the authentication process. Okay. And it requires between the client and the access point, it requires a server, a RADIUS server and a certificate authority. All right. So this is the authentication process. So at the beginning, basically it's very, very simple, a simplified authentication process. In practice, it has many more steps and much more information, but we just consider a simplified diagram of the authentication process. Sorry, why does it keep going to this? So at the beginning, the client wants to join the network, so it sends a message to start the process, right? And the access point will give the client the highest priority. Basically, it will block on all the requests until the authentication completes. The access point then asks the client for the identity. The client provides the identity. And then the access point sends the identity to the server to be authenticated, because this is where the credentials of the client is stored, all right? And then the server will work with the certificate authority to get certificates for the client. At the same time, the server sends the certificate back to the client because not only the network authenticates the client, but the client must also authenticate the network to make sure that the network is trustworthy, right? And the client can be sure that the network is trustworthy because the network has a certificate here, the server certificate, right? And the certificate is provided by a central authority. So you can imagine this as, let's say, someone issue a passport, right? So if you see another person's passport, a Canadian passport, you can be sure that that person is a Canadian, which is a good person, if we just have a simple argument like that. So the server sends a certificate to the client. So now the client knows that the server of the network is trustworthy. At the same time, the client would send its own certificate back. So now it trusts the network. So it sends its certificate to the access point, and then the access point sent to the server, and the server will verify this certificate to make sure that, again, the client is trustworthy as well. So after this, both of them authenticate each other. So now they can trust each other. The next step is to generate keys, and they need these keys for the access point and the client to communicate. Okay. So this is a very simplified process for accessing the key. The next one is basically this one is a simplified diagram. This one extends that part, okay? So at the beginning, the access point send a nonce to the station. So basically a nonce is a number used only once, okay? A nonce is a number used only once. And this one is used to prevent replay attack, right? So you can consider this as some kind of timestamp, right? So if this timestamp is at this time, another person replayed the message, the timestamp would become obsolete, so the replay attack cannot work. So it sends a nonce to the station, and then the station will generate its own nonce as well. So we have S nonce. So basically this nonce generated by the station. The station will combine the A nonce and the S nonce and other information to construct something called a pairwise transient key. All right, a pairwise transient key. And it will use one of the keys in here to generate a code called message integrity code, in order to make sure that this message cannot be tampered with. And if someone tried to modify this message, this code will help detect the modification. Okay, so this is the purpose of the message integrity code here, to make sure that the message is not tampered with. So it's sent back to the access point. So the access point again combine the S non, A non, and S nonce with all the information, construct the pairwise transient key. So basically, this is the same key here, all right? And then the pairwise transient key, will have many keys in it. We'll see later. And then the access point will generate a group key. right? So group key is used for multicast and broadcast. It will generate a group key and send back to the station. Sorry, it's not generate. It has a group key for multicast or broadcast. So it will send this key to the station. And this key is protected by this message integrity code, right? To make sure that the key is not modified. And then when the station receives this key, it sends back acknowledgement, okay? All right, so now we'll talk about how the keys are constructed, all right? So at the beginning, most of them share a master key, all right? Both of them share master key. And then the master key is combined with the access point information and the station information. And it goes through a function to generate something called a pairwise master key, PMK, right? And then the pairwise master key, again, is combined with the A-nons and the S-nons, right? So remember, we have the A-nons here and the S-nons here. That could be the A-nons here, S-nons here. The number used only once. And then it's combined with the access point MAC address, the station MAC address. All this information is combined. And then it will be fed into a function, a pseudo random number generator function to generate a pairwise transient key, all right? So this key is then divided into 3 keys. Okay. This key divided into 3 keys. Wait 1 second. Open the chat. So the first, this key here. Let's talk about this one. This is easy to understand. Basically, this one is used to encrypt messages between the station and the access point, right? So remember, every message have to be unicast message have to be encrypted. So this one would be used to encrypt those messages. Most of the messages between the access point and the station. This one here, key confirmation key. This is used to generate the message integrity code, right? It's used to generate message integrity code to make sure that, and it will be used here so that this message cannot be modified. And if it's modified, it will be detected, all right? And then this key here, key encryption key. This key is used to encrypt the group key. Remember when it sent the group key here, this group key must be encrypted. It cannot be sent as plain text because other people will know the key, right? So you must encrypt this key, and this key is encrypted using this key here, the blue key, all right? So basically a pairwise transient key will be decomposed into 3 components, and each has its own function, like I just said there, all right? And I think I posted a document. Basically, it's a document, a manual about different kind of keys here. In that document, you can read more about it in that document. Okay. Yeah. All right. And again, this is basically the same process we just said here. Okay. But now it shows more information. All right. So this one is to send A-nons, right? Remember the first one, basically it's this part, but now it contains more information, right? So the A-nons is sent here, right? And then the station will compute the PTK using the A-nons, S-nons, MAC address, both MAC addresses, right? And then the station send back the S-nons here, okay? And the access point receives the S-nons. It will perform the same operation here, okay? It will perform operation. It will get the PTK, all right? And from the PTK, it will get the this confirmation key. And this is used to make sure that there's no modification to this message, all right? and then it will take the multicast key and then encrypt this using this key here. All right, send back. Again, this message has the message integrity code to make sure that no one tampers with this. Okay, and to generate this message integrity code, we need this key. All right, and then this is basically acknowledgement. Okay, basically acknowledgement from the station. All right, so okay, so Savash, does that answer your question?
Yeah, that was very helpful. Yeah.
Yeah. All right. Okay, so let me, so no more question except from Joshua about ADCP. Okay. Right, so let me exit this. Share, let me go back to ADCP. Okay. Right. Share screen. Okay, so Joshua, can you see the screen here? Okay. We get the chat. Okay, great. All right. So is it the slide that you want lossy channel congested and then later we have disconnected, right? Okay. All right. Yes. Okay. So so at the beginning, both assume ADCP and TCP, they are in the normal state, right? Right. So they're in the normal state. And then at the sender, there is at least one packet with the retransmission timeout, which is about to expire, right? Or it expires. What it means is the sender sent this packet before, but never received acknowledgement. So that means it assumed that the packet was lost, right? Or it received 3 duplicate acknowledgements. All right, so remember 3 duplicate acknowledgement is equivalent to a negative acknowledgement. Basically, the receiver is telling the sender that I lost this packet, all right? Okay, and then if that happens, now when this happens, we also assume that sorry, 1 second, let me get the pen. We also assume that the flag ECN is false. Okay, it doesn't set, right? Sorry, can you wait just 1 minute? I'll be back. 1 second. Okay, yeah, sorry about that. All right, so all right, so now if this happens and we assume that this flag is not set, that means there's no congestion, right? So in this case, ADP assume that a packet is lost because of explicit congestion notification. Explicit congestion notification, okay? And this is done at the IP layer. So ADCP assume that packets, 1 or more packets are lost, but it's not because of congestion. it's because of, let's say, high bit error rate. It's because of a link break, for example. So in this case, what it does is it would tell TCP not to do anything. Okay, so TCP will be put in persist mode. Okay, so that means TCP should not do anything. Now, normally TCP would retransmit, right, the lost packet, and it will also reduce the window size as well, right? Remember we said about that, we reduce the window size. But in this case, TCP doesn't do anything because we don't want to reduce the window size. Okay. So, and in that case, ATCP will retransmit the segment in the buffer. Okay, so it will retransmit these packets. This packet or this packet. All right, it will transmit. And then when it after ATCP retransmit, if the receiver acknowledges these packets, right? So that means we have a new acknowledgement for these packets. Then in that case, ATCP assume that now everything is back to normal, right? ATC. So ATCP and TCP go back to normal. Okay. So question from Joshua. So TCP does the transmission, not the sender. Okay. All right. When we say TCP, the sender. When we say TCP does the transmission, mean the TCP protocol on the sender machine. All right, when we talk about sender, it's a big machine, it's a machine. And the machine will consist of many things. One of which is the TCP IP protocol suite, and TCP is part of that machine. Does that answer your question, Joshua? Okay, so when we say TCP, that means the TCP protocol on the sender machine, okay, on the computer at the sender, okay. All right, so when it receives it, it will go back to the normal state, okay. All right, so now we go to the next state, which is congestion. All right, so we assume that if congestion happens in the network, then one acknowledgement packet or data packet, the ECN flag will be set. Okay, so we know that there's congestion, and in that case, this is actually congestion, right? So that means ATCP now does not interfere with TCP congestion behavior. It just stays quiet, and it lets TCP does TCP's job, which is to transmit the new segment, right? And reduce the window size as well. Okay, receive ECN, right? And then when TCP transmit a new packet, that means TCP reduces the window size, retransmit lost packet, and transmit a new packet. That means everything is back to normal. Okay. All right. So that is the congestion problem. Now the next problem is disconnect, right? So that means when the network is partitioned into two parts. So let's say we have a bunch of nodes here, right? And for some reason, let's say this part and this part move away from each other. So let me the distance here become very far. All right. So let's say somehow they moved, and that's why the network is disconnected into two parts. So in that sense, if you have someone here trying to send a message to this node here, let's say this is A, and this is B, it cannot reach because the network is partitioned or disconnected here. All right. So in that case, at the IP layer, let's say the message will go to this, and then this should be transmitted to this, and this should be transmitted to this. Now this node here cannot reach the destination. So it will generate an ICMP message, destination unreachable. And then when ATCP here, ATCP at A receive this message, it will enter the disconnected mode, right? And at the same time, TCP is put into the persist mode. And when they are in this mode, they don't do anything, right? And it makes sense because they don't do any congestion control. They don't retransmit. They don't transmit anything. They stop all transmission. And it makes sense because there's no route, no path to transmit anything, right? So they don't transmit anything. They don't do anything. But the window size is set to 1, right? Because when these two networks are reconnected, we have to build a new route. Basically, we reestablish a new connection. So in that case, we have to set the correct value for congestion window. So that's why we set this to 1, and then we probe for the correct value later. Okay. At the same time, TCP periodically generate probe packets to reconnect with the receiver, right? So basically, it keeps asking, are you there? Are you there, for example, right? And if the receiver now is connected back to the network, let's say now they move, these two move close to each other, then the receiver will respond to this probe packet, and then we reestablish the connection, and the receiver respond with a duplicate acknowledgement or data packet. All right, and now the route is established. ATCP and TCP can return to normal state. Okay, and when they return to normal state, TCP will start the process of building the congestion window. Remember, we start from 1 and we increase to 2 and then 4, right? And then 8, remember that? TCP will start this process again in order to get the correct value for the window, congestion window. Okay, and this is the illustration. It received destination unreachable, right? Go from congested to disconnect, or from normal, from normal to disconnect, or from lost to disconnect as well. And then when it's receive duplicate acknowledgement or a packet, it go back to the normal state. All right. Okay, and this is the same diagram in black and white. Okay, so does that answer your question, Joshua? Okay, so I suggest you read the paper. I just uploaded the paper on eClass. Okay. If you don't get all the details, you read the paper. You have to read the paper because, to be honest, I didn't even mention all the details of the implementation. I just mentioned the high level details. You have to read the paper to get most of the detail. Okay, right, and that will so if you go to eClass, so let me stop share here. Right, and you go to the end of the page under the slides, and don't forget to refresh. You will see ATCP paper. Okay, yeah, all right, you're welcome. You have to read the paper. Okay, after you read the paper, you understand much more. I can assure you of that. All right. Okay, yeah. But there will no TCP will not be in the test tomorrow. All right, so if you want to read it tonight, that's fine, but it will not be in the test tomorrow. It will be in the final exam. All right, any more questions? Okay, Savas, you have a question?
Yeah, actually, I had another question about PCF. And I wanted to ask, I asked the same question from the TA, but he had no idea as well. Can you, like, would it be possible to briefly explain what is PCF exactly? Because on the slides, there is no description about what is the point of PCF.
On the slide, okay, let me go to
on WLAN slides.
Okay, wireless LAN, right?
Yeah, on page 40, 44, 43, 44.
Let me Just trying to. Okay, I see. Okay. Right. So, what's page? What slide number is it?
43.
43. Okay. Okay.
So the next slide, I mean 44, is about the structure of the PCF superframe.
No, it's a structure. Yes, yes. Okay. Yes.
So the first question is, what is PCF? And the next question is, how can you like briefly describe this figure on page 44 as well?
Okay. All right. So one second. So let me share the screen first, and then. Okay. So so this is AO 2.11 medium access control, right? So the time of the medium, or the in the network of the medium, coordination function, or it's a period in which there's no contention. Basically, the first part here is the centralized medium access control scheme. Okay, so it's media centralized in the sense that there's a coordinator that will decide who will use the medium next, right? And the second part of the superframe is the distributed coordination function, DCF. So this is the DCF is basically the CSMACA protocol we'll talk about before, right? We have RTS, CTS, data acknowledgement, right? And then we have back off time, and then we wait for the back off, we draw a timer, and then we wait until the timer expires, and then we transmit. So that would be DCF, all right? And PCF is when the coordinator will decide who can transmit next, all right? And of course, at the beginning, we have a beacon message to synchronize the beginning of every superframe, okay? Does that answer your question?
Yeah, so from my understanding, is PCF kind of just kind of function deciding who should transmit next? And so, and is it correct that PCF and DCF both are something inside the IEEE 802.11 package, right? Is it
yes.
correct?
Yes, that's right. Yes, both of them are in AO 2.11 standard. Yes, that's right.
Okay, got
yes.
it.
Yeah.
Thank you.
Yeah, you're welcome. And then the operation of PCF is here, right? You know that, right?
Yeah, I think there was a question on the practice questions as well, asking about a kind of to draw a flow diagram, something like that.
Yeah, that's right. That's right. So you have different let's say different transaction, right?
Yeah, there was a receiver, an access point, and 3 transmitters, I guess. And the question was asking to draw the flow diagram of these connections. So and I was seeing the CF poles, CF end,
right
in the graph. So do we have the answer to the question is something like this page, right? In this, like this figure.
Yes, exactly. Right, exactly. Yes.
Fine. Thank you.
Yeah, you're welcome. Yes. Okay, any other question? All right. So yeah, so I guess there's no more question. There's a question from Ismail. Do you have a question, Ismail? Okay, all right, so that's good. Yeah, so yeah, to do that solve that problem, you draw this kind of diagram, right? Okay. Can you solve one of the practice question? There's so many. I think you can try one and then see. I'm not sure which one to solve. For example, let's say I just pick randomly. So let's say the second problem in the first section, CSMACD. Describe the CSMACD algorithm using a flow diagram. Okay. All right. So question 9 for medium access control. For medium access control. Question 9 is, what is the exposed terminal problem? 10, sorry, for 10, I cannot draw on the diagram here. I don't have, so for question, yeah, I can give you a hint. For question 10, you can use, you draw something similar to this. I can show you the diagram and then you can, okay, all right. So you see this? For 10, you draw something similar to this. Okay, and I cannot draw here because I don't have anything to draw, but you draw a diagram similar to this. Okay, so it's very similar to this problem. Yeah. All right. Just very similar to this problem. We just change some number and that's it. Yeah, but it's very similar to this problem. Okay. All right. So any other question? So yeah, so in that case, good luck with your study and I'll see you tomorrow. Okay. All right. So have a nice evening and good luck with your study. Okay. Bye for now.